Have you ever looked at a 3D engineering drawing and wondered how do engineers convert this into accurate 2D views? Many students struggle when they see sectional views, hidden features, and projections. But what if you could easily convert any 3D object into top view and sectional front view step by step? In this video, I will show you exactly how it is done using a simple mechanical component drawing method used in engineering graphics. When we look at a 3D pictorial view, everything looks clear because we can see the object from multiple directions. But engineering drawings require us to show the object using 2D orthographic views. These views help machinists, designers, and CNC operators understand the exact shape and dimensions of the part. Today we will learn how to create times the top view times the sectional front view from a given 3D isometric drawing. Before drawing anything, the most important step is analyzing the object carefully. Let's look at the key dimensions. The object has times total length is equal to 75 mm, times total width is equal to 50 mm, times total height is equal to 50 mm. There is also times a semicircular profile on one end, times a cylindrical hole of diameter 12 mm, times a central rib with thickness 12 mm, times a rectangular slot on the base. Understanding these features first makes the drawing process much easier. Now let's talk about the sectional view. In engineering drawings, sometimes internal features cannot be seen clearly. To solve this problem, we use a cutting plane. Imagine slicing the object with a saw. Everything in front of the cutting plane is removed. What remains shows the internal structure of the object. The areas where the material is cut are filled with hatching lines at 45 degrees. These lines represent solid material. Empty spaces such as holes or cavities remain blank. Drawing the top view. We begin with the top view. Start by drawing the base rectangle. The size of this rectangle represents the footprint of the object. So draw a rectangle of 75 mm length, 50 mm width. This rectangle defines the outer boundary of the top view. Always draw light construction lines first, because we may need to adjust them later. Before we pick up the pencil, we must analyze our object. We are working with a component that is 75 mm long, 50 mm wide, and 50 mm high. It features a semicircular profile, a 12 mm cylindrical hole, a central rib, and a base slot. Understanding these features is the secret to a perfect drawing. We always start with the top view to establish the footprint. The base, draw a rectangle 75 mm long by 50 mm wide. Use light construction lines first. The profile on one end, locate the center and draw a semicircular arc with a radius of 25 mm. This fits perfectly across the 50 mm width. The hole at that same center point, draw a circle with a 12 mm diameter. The rib and slot, finally, draw the 12 mm thick central rib connecting the cylinder to the base and mark the rectangular slot on the opposite side. Now that our map is ready, we use vertical projection lines from every corner, hole center, and edge to move upward into the front view. This ensures 100% dimensional accuracy. Now, let's talk about the sectional view. Imagine a cutting plane slicing through the center of the object. We remove the front half to reveal the internal structure. The base, mark a base thickness of 12 mm and draw a horizontal line. The height, extend the cylindrical section to its full height of 50 mm using your projection lines. The internal hole here is the key, because this is a sectional view. the internal hole is no longer hidden. Draw it with solid object lines. It will appear as a rectangular opening where the cutting plane passed through. Finally, we apply hatching. Draw thin, uniform lines at a 45-degree angle across all areas where the saw would have cut through solid metal. Remember, do not hatch the hole or empty spaces. Finish your drawing by adding standard dimensions, overall length, width, height, and hole diameter. By following these steps, analyze, project, and section, you can master any engineering graphic. This technique is essential for anyone in mechanical design or CNC programming. Project lines. This allows us to dimension the 12 mm internal hole and the central rib directly, ensuring the part is manufactured exactly to spec. Precision starts with the cutting plane line. In your top view, draw a thick dashed dot line through the center of the hole and the rib. Add arrows pointing toward the front view. These arrows tell the viewer which direction we are looking. Now, let's refine the projection method. Vertical alignment. Every feature in your top view, the 75 mm base edges, the 12 mm rib walls, and the 12 mm hole limits, must align perfectly with the front view above it. The base versus the boss. Note that the base is only 12 mm thick, but the cylindrical boss rises to a total height of 50 mm. The transition, where the 12 mm rib meets the cylinder, the projection line ensures the tangent point is mathematically accurate. Hatching is where most students lose marks. Think of the hatching lines as a signature of solid material. Rule 1. Use a 2H pencil or a thin line weight for hatching. It should never be as thick as the object's outline. Rule 2. Maintain a consistent 45-degree angle. If you change the angle midway, it suggests a different part or material. The rib exception. This is a professional secret. In many standards, thin features like ribs or webs are not hatched, even if the cutting plane passes through them. This prevents the drawing from looking too heavy and misrepresenting the part's strength. Before you finish, verify your dimensions one last time. Does the 50 mm height in the front view match the scale of your top view? Are your arrowheads sharp and touching the extension lines? Mastering these sectional details is what separates a student from a professional designer.